Hi, welcome to today's talk on changing momentum and impulse. What are we learning? We're going to learn how we change momentum, and we're going to relate impulse to changing momentum. First, let's review what we mean by momentum. Momentum is the quantity of motion, and it is defined as the mass times the velocity. It is a vector quantity. The units are kilograms meters per second. Let's review what we mean by impulse. Impulse is the force times the time. It also is a vector quantity. The units of impulse are also kilograms meters per second. We did see that we could also call this a Newton second, but those are the same. So how can we change momentum? There are only two variables in this equation, so that leaves us with either changing the mass or changing the velocity. When an object's moving along, the mass usually stays the same. One example where it doesn't could be the rocket equation, which we'll look at a little bit later, but on the most part, our object's mass will stay the same. What usually changes is the velocity. If we want to change the momentum of an object, we must change the velocity. The rate of change of velocity is the acceleration. Acceleration requires a net force. In other words, acceleration is the net force divided by the mass. Acceleration is also the rate of change of velocity. If we take this part of the equation, delta V over t, and this part of the equation, the net force divided by the mass, multiply both sides by time, multiply both sides by mass, and we wind up with this equation here. The mass times the change in velocity equals the force times the time. The change in momentum is going to be the mass times the final velocity minus the mass times the initial velocity. We can rewrite that as mass times delta V, or the change in velocity. Remember that our impulse is force times time, and that equals the change in velocity. So the impulse of the force acting on an object equals the change in its momentum. Let's look at an application of this. Let's say we have a car, and it has some momentum because it has mass, obviously, but it has some velocity, and it's moving along. Now we're going to bring it to a stop over a long period of time by running it into something nice and soft, say a bunch of hay. This means that the time that we took to slow this car down was very large. The force on it will be smaller. Let's look at another example. Let's say we have this car moving along. It has momentum. Now we're going to bring it to a stop very, very, very quickly by running it into a wall. Now, the time that we took to slow this car down was very, very small. The force was very large. In both of these cases, we are changing the momentum, and we are equating that to the impulse, force times time. The change in momentum, going from some momentum to zero momentum, will be the same, and we can change that momentum by either applying here a large force with a small time, or a large time with a small force. Here's another example. I'm going to drop an egg into this beaker here. When the egg hits the bottom of the beaker, it will lose that momentum very, very quickly with a short amount of time and a large amount of force. Now I'm going to drop the egg from the same height, and this time it's going to fall into a beaker full of water. The water is going to take a little bit of time to slow it down. It will be less force, more time. And we can see the difference it made in the effect on the egg. The egg does not break because it had less force over a longer time than in the water, that is, than the egg did when it hit the bottom of the glass. Now let's take a look at the mathematical relationship between momentum and impulse, and in particular, the change in momentum. Call this the impulse momentum theorem. So our impulse is force times time, which is our change in momentum, which means that that's our mass times the final velocity minus mass times the initial velocity. Let's try this out now. Here's a classic example. We have a golf ball, and the golf club is going to hit it. The golf ball is initially at rest. It has a mass of 5 times 10 to the negative 2 kilograms. After the contact, it's going to have a velocity of 44 meters per second. What is its impulse? Well, let's write down our equation. The impulse is the force times the time. Now, do we have the force? No, we don't. Do we know how long we're in contact here? No, we don't either. Can we find the change in momentum? Well, if it was at rest and then it went to 44 meters per second, we certainly can. Our change in momentum is the mass times the final velocity minus the mass times the initial velocity. Let's plug that all in. Notice that our initial velocity was 0, and we get our change in momentum is 2.2 kilograms meters per second. That's our impulse. Our impulse is the change in momentum. Once we found the change in momentum, we knew the impulse. All right, let's take a look at what we know now. First, a review of momentum and impulse. Our momentum is mass times velocity. Our impulse is force times time. They are both vector quantities. Our change in momentum is mass times the final velocity minus mass times the initial velocity. Again, only the velocity is changing. And finally, our impulse momentum theorem. The impulse is force times time, which is our change in momentum, which is mass times final velocity equals mass times initial velocity. Probably the most useful form of all of this is that the force on an object times the time that force is being applied is going to equal to the mass times the final velocity minus the mass times the initial velocity. All right, thank you for listening. Rewind and review as necessary. Don't forget your Cornell notes.